So Spintronics, is an element in controlling the spin on the electron, and becomes an element of quantum computing, for example. If you just take the electron and spin polarize it, you immediately have a bit spin up, spin down, right? The real benefit is massively parallel systems. So if you take two quantum dots where you can control the spin, right, then you can end up with some type of multi-level computing system due to the spin interaction, but it's a quantum mechanical process, which is it's a quantum mechanical process, and most of that happens in what they call fridges, very low temperatures, so Kelvin fridges. A lot of our Spintronics work is that we're trying to make devices that work closer to room temperature, so they'll be useful for quantum computing. Also, some of those elements, if you make spin valves and other things, can be used in neuromorphic computing. So you have one, quantum computing, and the ability to have multi-level systems, and then you can also have neuromorphic computing that starts modeling the brain. Hopefully not my brain, but you can model the brain and brain synapses. I think it's really enabling technology for quantum computing and neuromorphic computing.
Okay, sir. One more question by one of the participants. What will be the scope of photovoltaic thermal collector?
That I don't know. So if you actually look, when you look at thermoelectric devices, they have a thing called the KT. And that is an equation which ties into the Seebeck coefficient squared. It's electrical conductivity divided by its thermal conductivity. I always split those up. In semiconductor materials, your thermal and electrical conductivity actually track with each other. So as you try and improve one, you improve the other, so your overall ratio doesn't change. So to make something which is going to be efficient as solar, you need something with a KT of about 2 or so. Most of these devices have got to about a KT of about 1 or so. They tend to be in complex materials such as scudderites, because you're trying to control the lattice vibrations within the material. And these scudderites have dangling bonds in that. We've done some work, which I didn't cover here on the oxide, where we can get materials that work with reasonably good efficiencies in KTs beyond 1, maybe up to 2. So once you have that, when you have a concentrated device, you can start looking at, rather than only just having multiple junctions, also extracting heat out of the device as well. But those device structures are more complex than a simple PN junction.
Okay, sir. There's one more question. Why is there still traditional energy based on burning minerals in some countries?
I believe that you burn minerals in your country. Is that right? So your question is poorly worded. It's all countries, right? It's actually all countries, because whenever I visited India, they've got cars and that. Yes. That's our pre-existing infrastructure, right? It's what was easy to do. It was easy to extract oil, which was prevalent. And if you think about it, mineral-based oils and that really comes from the sun at the end of the day, and it's stored energy, from the sun. When we're going to solar, we're using the energy that's coming into the earth at this particular time. But that's more of a philosophical question than really a scientific or engineering question. And something that the students are going to actually have to that you students are actually going to have to address in your lifetime.
Okay, sir.
So what's fabrication challenges in making 3-5 materials? Are they safe for in-house use, you already have them in your house, right? So if they weren't, I brought up the chat so I can read off. If they weren't, right, you wouldn't have lasers in your house. Many lasers are gallium arsenide-based materials. Arsenic by itself is incredibly toxic, but when it's bonded, it isn't. There's really not that many issues because the materials you make are very stable. And like silicon, where you have a covalent bond, when you move to 3,5s, right, that bonding or that sense of covalent bonding in materials is still very strong. So these materials are very safe. The issue tends to be when you grow gallium, gallium nitride, gallium. Gallium is somewhat limited. Indium is worse. So as you actually go to materials that are heavier, one, they do tend to become more toxic, and secondly, they have more limited variation and availability. And I think indium comes out primarily as a byproduct of aluminum smelting, for example. And a lot of indium and other things is actually based in China. So there's these global economic drivers as well as for what materials you're using. So we've also been doing work in, we can also be doing work in 2,6 materials. I've got a whole body of work in zinc oxide materials. So zinc is a prevalent material. Oxygen, I think if you're not finding oxygen at this point, you're probably in trouble. You won't be around. But zinc's prevalent materials like silicon, prevalent material. That's why the silicon industry came in. So our zinc oxide-based materials do provide some other solutions. And zinc oxide, for example, is used in sunscreens, in ointments, and that. So it's things that have been used for an extended period of time already. So there is a possibility to turn those into other materials. So can electricity be generated by cooling a photovoltaic cell? Yes. So that's what I talked about before. But it isn't. It's cooled. It's cooled by extracting the heat. And if you take a piece of semiconductor material, it's called Fick's law. If I warm it up, I produce a whole pile of intrinsic carriers. And then if I take that heat away or extract that heat, it wants to go back to equilibrium. So that process of driving you back to equilibrium is what produces the current. How to charge a lithium-ion battery on a lunar rover? Same as here, right? Same as here. The only thing that you may look at then is how does the power spectrum, right, the radiation change on the moon, on Mars, or in other places compared to what we have on the Earth. Remember, on the Earth, we have a number of different stratospheres that absorb energy at different points. Ionosphere absorbs all energy between like 285 nanometers to 265 nanometers. Water vapor, our nice power spectrum that I showed before, has all these dips due to absorption and due to water vapor in the atmosphere. So you'd look at you would look at what the actual solar spectrum is, and you would design for that.
Yes. Any more questions?
No, I'm starting to run out of time.
Okay. Yes, I think we can conclude.
Let me tell you a little bit about our college, Kennesaw State University. The College of Engineering is about 5,100 students now. We're currently in the process of growing up to about 6,000 students in the next couple of years. We have one of the first robotics program in the country. I think we were the third to go through APEC accreditation, the second largest robotics program in the country. We have our traditional, mechanical with an aviation minor, a nuclear miner. We have electrical and computer